All right. Today we're talking about differentiability, which is just the topic of when is something differentiable? When can I take the derivative and get an answer? Okay. Yesterday, we alluded to when that would happen a little bit in our pictures, but there are more places than just what we talked about yesterday. So this kind of gives us a little chart of when things won't have a derivative, okay? So the 4 different places that something would not be differentiable would be the one we kind of alluded to yesterday. Anytime your picture has a corner in it. And that could be a piecewise that forms a corner. That could be just a function that itself creates a corner. For example, y equals the absolute value of x. Where that corner occurs is where it would fail to have a derivative or not be differentiable. So at x equals 0 in this picture, that one would not have a derivative. A cusp is not probably a shape we've seen very often, but a cusp is created by an equation that looks something like y equals x to the 2/3, and it is kind of like our absolute value graph, but curvy as it heads towards that point. And again, at where that point is happening is where our graph is not differentiable. So again, in that picture at x equals 0. Okay. We have been talking a lot about tangents to our graph, right? Because that is the slope of the tangent line is our derivative, right? Your derivative is the slope of the tangent line. Well, when our tangent becomes a vertical line, it stops being differentiable there. Why? Well, what is the slope of a vertical line? Undefined, right? So doesn't it make sense that if it's undefined, it doesn't exist? That's why if our tangent becomes a vertical line, it is the derivative does not exist. So where would that happen? When it's something like this, if you can picture your parent graphs back from pre-calc, that would be a zoomed in picture of like a cube root of x. Well, right there at 0, if I were to draw in the tangent line to this dot right here, the tangent line to that would be a vertical line. And so when your tangent line becomes vertical, the derivative does not exist because the slope of a vertical line is undefined. The last one is if our graph has some sort of discontinuity. Remember, we've got lots of options for discontinuities. We've got infinite, removable, and jump. The example I have up here is a jump discontinuity. Any type of discontinuity is going to create a point of not being able to differentiate. The greatest integer function would be an example of one of those. There would be your discontinuities. We've got several places that are not differentiable in that picture that I just drew. Every place that it is discontinuous. And remember, that works for all of our discontinuities. If we've got a vertical asymptote in there, if we've got a hole in our graph, any sort of a break in our graph is going to mean that it is also not differentiable at that point. So part of what you guys are going to start with is being told that something is not differentiable, and how do we prove it? Well, the reason or the way we are going to prove it is we're going to approach that particular x value. So let's look at this first example. It is not differentiable here at 0. And one of the things is if I were to look at the piece of the graph that is to the left of that point and the piece of the graph that is to the right of that point, do you see how their tangent lines, which in this case would actually just be the line of the graph, don't have the same slope? And when they meet up at this x value, since those slopes don't match up, those derivatives don't match up, that's why it does not have a derivative at that particular point. So what we use is what's called our left and right hand derivatives at particular points to show that it is not differentiable. So again, look at the directions on the top of this one. Compare the right and left hand derivative to show that the function is not differentiable at point P. So they're already telling us this is not differentiable. Can you see where it's not differentiable? Right here where it's got kind of a corner looking thing. So in this one, point P would be at 0, 0. And we are looking at the x value of that. So at x equals 0, we're going to show that the derivative for each of those two different functions that we see up there don't match. Okay? So you just do them separately. When I do the left-hand derivative, I use the function that is left of whatever point they're asking me to look at. So point P is at 0. The function to the left of that is negative x plus 3. So I just do the derivative of negative x plus 3 at x equals 0, whatever x value was in point P. Okay? So we go through our formal definition. This one is slightly confusing, and I don't want you to get confused. Your formal definition is always going towards 0, h going towards 0. The only reason I'm using 0 for the x value on this one is because that's the location of point P. That will change per problem. Okay? P can move anywhere in the graph that they're saying it's not differentiable. We use that x value when we set up our derivative. Okay? So now I write out my function at 0 plus h, and then I write out my function just at 0. All over h, and just like normal, we would clean that up. Okay, well, 0 plus h is just h, and then the negative out front makes that a negative h. And then 0 plus 3 is just 3. The negative out front makes that a negative 3. Take one more step in my simplifying here. Let's see, 3 minus 3 is gone. And then we're at h over h, right? Well, negative h over h. Aren't your h's going to simplify down to just 1? And the negative out front is actually going to simplify down to negative 1. Well, again, the limit of a constant is not going to change that constant. So yes, I am doing direct substitution. There is no h to directly sub it into, so it doesn't change it. Our left-hand limit is negative 1. Our left-hand derivative is negative 1. Look at the left-hand side of our graph. Doesn't it have a slope of negative 1? Okay. Then we repeat this process and do our right-hand derivative. And again, to do the right-hand derivative at point P, I use the piece of graph that is just right of that. So I would use, in this case, x squared plus 3. And again, we are doing this at x equals 0 because that is the x value of point P. Set up my formal definition here. So first time through, I'm going to plug in 0 plus h. Second time through, plug in just 0. Clean it up. 0 plus h is just h squared is h squared. 0 plus 3 is 3. Distribute that negative. 3 minus 3 is gone. H squared over h will simplify down to just h. And then I can directly sub in 0. Well, when I directly sub in 0 to a just h, it's just 0. And then I have shown, now remember, I'm showing that our derivatives are different than each other, right? The right and left-hand derivatives are different, which is why when I get to that x value, it is not differentiable because I don't get the same answer on both sides of it. If it was differentiable, I would have gotten the same answer for both sides of that derivative. Any questions? All right. Moving on, given a picture like this one, we're going to talk about where it is differentiable, where it is continuous, and etc. So looking at this, it says, at what domain points does the function appear to be A, differentiable, B, continuous but not differentiable, and C, neither continuous nor differentiable? Okay, so if we look at that picture, let's talk about the whole differentiable thing. At the beginning of our notes, we talked about things that are going to make it not differentiable, right? So run through those 4 options. Does this picture have any corners? No. Does this picture have any cusps? No. Does it have any, and this one you got to think about for just a second, does it have any vertical tangents? I'm going to go with no. No vertical tangents on this one. Does it have any discontinuities? Do we have any vertical asymptotes, removable holes, or jump? Okay. So if none of those things happen, it's going to be differentiable everywhere. So we would say that what domain points is it differentiable? It is differentiable on the entire domain, -2 up to 3. Okay, so differentiable the whole time. Okay, well, if it's differentiable the entire time, where is it continuous but not differentiable? Nowhere, right? Because it is differentiable everywhere. So there are no points where it is continuous but not differentiable. And then neither continuous nor differentiable, same thing, because it is differentiable the entire time and continuous the entire time. There are no points that it is neither of those. Okay, so that was a pretty simple example. Let's look at one that actually has some answers up here that we can talk about. Okay, next one. At what domain points does a function appear to be differentiable, continuous but not differentiable, and then neither continuous or differentiable? So a little bit different of a picture. So again, start with a question on differentiability. If I'm looking at where is it differentiable, I'm looking for those 4 options that makes it not differentiable. Okay, so let's just run through those 4 options. Is there anywhere that it has a corner? Yes, so that would be one place that it is not differentiable. So it's not differentiable. So it is differentiable on its domain from, what is that, -2 to 3. Except, and we're going to find the places it's not. There is a corner at -1. Okay. Next one, are there any cusps in that picture? No. Are there any vertical tangents? No. Are there any discontinuities? Yes. So as we trace on here, I get a jump discontinuity at x equals 0. So a discontinuity at 0. Continue tracing, we have a hole or a removable discontinuity at 2. So what I've created for myself is a list of places that it is not differentiable. It's not differentiable at -1, 0, or 2. As you go on to answer the rest of these questions, that's basically your word bank. Those are your answers for the next couple of questions, because the next couple of questions are kind of categorizing those different places of not differentiable. So of those options, were any of them continuous in our not differentiable options? Meaning, could I have continued tracing without picking up my pencil? Yeah, which one? -1, right? At the corner, I don't have to pick up my pencil. I can keep tracing, which means it's continuous, but not differentiable at that corner. So yes, at x equals -1. How about at the next one? Not continuous, not continuous. So think about your options at the beginning. Corners are going to stay continuous, right, but not differentiable. Cusps would be the same thing. And actually, the vertical tangents would be the same thing too, because I'm not picking up my pencil on any of those. It's that last category here, neither continuous or differentiable. So any of those times that it was discontinuous that made us say not differentiable, go in that last category. So any of our infinite, removable, and jump spots in our picture are going to be in that third option where it is neither continuous or differentiable. So at 0, where it was a jump discontinuity, and at 2, where it was a removable discontinuity, it would fall into that last category that is neither continuous nor differentiable. Any questions on that? So in the top one, it's asking you to identify all of the places not differentiable, and then categorizing them below that, whether it was continuous or not continuous at that particular point. Okay? All right, the last thing I want to put up here is a very important topic for us, and it's going to be a little bit more important as we go through this. But if you are ever told that something is differentiable, it automatically means that it has to be continuous. Doesn't that make sense? Because that was one of the things that would make it not differentiable if we had a discontinuity. So if they say you are looking at a differentiable function, you get to assume that that function is continuous on the entire thing. Now, what is that going to mean to us eventually? Well, if you think back to some things that we've used before, do you remember like our intermediate value theorem? One of the things we always had to confirm before we could use it was that it was a continuous function. Well, now a second way of them telling us that something is continuous is they can tell us that it is differentiable. So if they say it's differentiable, we get to automatically assume it's continuous. Now, is the reverse true? If they tell us that it is continuous, do we get to assume that it is differentiable? No. Take that quick trip back to honors geometry that we loved so much back in the day. You guys remember those whole biconditional statements? There was a whole chapter right at the beginning of the year. You know, the if-then, if and only if. This is not a biconditional statement. It does not work the other way around, okay? Just because it is continuous, a cube root of x graph is continuous, and it is not differentiable at every point. So just keep that in mind. It is not a biconditional statement. It doesn't work the other direction, but if it is differentiable, it has to be continuous the whole time. Any questions on that? All right. Your assignment tonight is, again, out of the book. You are on 114, doing 1 through 16. Make sure that when you guys are looking at the first part that is asking you to do the left and the right hand derivatives to show that it is not differentiable, that you're showing the work, okay? The setup is a point. The answer is a point. So make sure that we've got those things at a minimum as we are doing left and right hand derivatives.